Every version of concrete. Used in construction. Ordinary Portland cement concrete. This is the type most people picture when they hear the word concrete. It's made by mixing cement, water, sand, and gravel, and it has been the backbone of construction for over a century. The cement acts as the binder, and when water is added, a chemical reaction called hydration begins, gradually hardening the mix into a dense, solid mass. The process takes time. Full strength is typically reached after 28 days, but the result is a material that is affordable, widely available, and consistent enough to be trusted on job sites across the world. It's used in everything from sidewalks to apartment buildings, and its reliability is the reason it became the global standard. Reinforced concrete. On its own, concrete handles compression well, but cracks under tension. Pull it, bend it, or stretch it, and it fails. Engineers solve this by embedding steel bars, known as rebar, directly into the mix before it sets. The steel takes on the tensile forces while the concrete handles the compression, and together they behave as a single structural material far stronger than either alone. The placement of the rebar is not random. Engineers calculate exactly where tension will occur and position the steel accordingly. Almost every modern building, bridge, and overpass depends on this combination in some form, and it remains one of the most important developments in the history of construction. Prestressed concrete. This takes reinforcement a step further. Instead of simply placing steel inside the concrete, engineers either stretch the steel under tension before the concrete is poured, or apply tension after it has hardened. This puts the entire concrete element under a permanent compressive force, which counteracts the tensile stresses that would normally cause cracking under load. The concept was developed in the late 19th century and refined throughout the 20th, gradually becoming essential for large-scale infrastructure. It allows for longer spans with thinner sections, which is why it's widely used in highway bridges, parking structures, and large-span roofs, where both efficiency and strength are critical. High-performance concrete. Standard concrete has limits. When projects demand greater strength, durability, or resistance to harsh environments, high-performance concrete steps in. It uses carefully controlled mixes with lower water content and often includes supplementary materials like silica fume or fly ash, which fill microscopic gaps in the structure and make the final product denser and more resistant to damage. The lower the water content, the stronger and less porous the result, but achieving that balance requires precise engineering. Offshore oil platforms, major bridges, and high-rise foundations often depend on it because the consequences of material failure in those environments are simply too great to accept. Self-compacting concrete. Pouring and compacting concrete in tight or heavily reinforced spaces is difficult. Vibrating equipment is normally used to remove air bubbles and ensure the mix fills every corner. But that process takes time, requires skilled operators, and can still leave voids in complex formwork. Self-compacting concrete flows on its own. Its mix is specially designed with carefully adjusted proportions and chemical admixtures that give it a fluid consistency without causing the aggregates to separate. It spreads, fills, and settles without any mechanical effort, making it ideal for precast elements, densely reinforced sections, and architectural concrete where surface finish matters as much as structural performance. Lightweight concrete. Standard concrete is heavy, and in some applications, that weight creates problems. Lightweight concrete replaces normal aggregates with materials like expanded clay, pumice, or foam beads, significantly reducing the overall density. It doesn't carry the same structural loads as conventional concrete, but it performs well in non-load-bearing walls, roof decks, and insulating panels. Its lower thermal conductivity also makes it useful in applications where energy efficiency matters, as it slows the transfer of heat through walls and floors. In tall buildings especially, reducing the weight of non-structural elements adds up quickly and can meaningfully reduce the load on the entire structure below. Heavyweight concrete. On the opposite end of the spectrum, some applications require concrete that is far denser than normal. Heavyweight concrete uses aggregates like barite or magnetite, which are significantly denser than standard gravel, resulting in a material that can be twice the weight of ordinary concrete per cubic meter. This density is not about strength, it's about mass. The resulting material is used primarily for radiation shielding in nuclear power plants, medical facilities, and research reactors, where the thickness and density of the walls determines how effectively radiation is absorbed and blocked from surrounding areas. Fiber-reinforced concrete. Rather than using large steel bars, this type distributes reinforcement throughout the entire mix in the form of small fibers. These fibers can be made from steel, glass, synthetic polymers, or even natural materials like basalt, and they are mixed in uniformly before the concrete is poured. They work by bridging small cracks as they begin to form, preventing them from spreading and giving the material a more ductile character, meaning it bends slightly before it breaks, rather than failing suddenly. This behavior is particularly valuable in industrial floors subject to heavy impact, in shotcrete linings, and in precast panels, where thin sections need to resist cracking during handling and installation. Shotcrete. This is concrete applied by force through a high-pressure nozzle rather than poured into forms. The mix is projected at high velocity onto a surface, where it compacts on impact and adheres firmly without the need for traditional formwork. There are two methods: the dry mix process, where water is added at the nozzle, and the wet mix process, where the concrete arrives ready mixed. Each has its advantages depending on the scale and conditions of the job. Shotcrete is used extensively in tunnel linings, slope stabilization, swimming pools, and the repair of deteriorating concrete structures, particularly in locations where setting up conventional formwork would be impractical or impossible. Pervious concrete. Standard concrete is essentially waterproof, and when it covers large surface areas, it prevents rainwater from soaking into the ground, increasing runoff and placing pressure on urban drainage systems. Pervious concrete is designed to do the opposite. Its mix uses very little fine aggregate, leaving an open, porous structure with interconnected voids that allow water to pass through directly into the ground below. It's used in parking lots, driveways, and pedestrian paths, where managing stormwater is a priority. In cities dealing with flooding or water table depletion, this material offers a straightforward way to let developed land continue functioning more like natural ground. Geopolymer concrete. Producing ordinary Portland cement releases a significant amount of carbon dioxide, roughly 1 ton of CO2 for every ton of cement manufactured. As construction volumes have grown globally, that number has become impossible to ignore. Geopolymer concrete replaces cement entirely with industrial byproducts like fly ash or slag, which are activated by alkaline solutions instead of water. The chemical reaction that binds the material together produces far less carbon, and in many cases the resulting concrete matches or exceeds the durability of conventional mixes, with better resistance to heat and chemical attack in certain conditions. It represents one of the more serious and scalable efforts the construction industry has made toward reducing its environmental impact. Ultra-high performance concrete. This is where concrete reaches its current limits. Ultra-high performance concrete combines an extremely low water-to-cement ratio, very fine aggregates, high volumes of steel fibers, and supplementary cementitious materials to produce a material with compressive strengths many times greater than standard concrete. It is also nearly impermeable, highly resistant to abrasion, and capable of spanning longer distances with sections thin enough that they barely resemble conventional concrete construction. Developing a working mix requires extensive laboratory testing and tight quality control, and the material costs significantly more than conventional options. But in bridges, blast-resistant structures, and high-precision architectural facades, it allows engineers and designers to achieve forms and performance levels that would simply not be possible with anything else available today.